Alright, in this video we're going to be looking at trying to get a handle on the differential mode gain of our simple 5-transistor differential amplifier using the node fixing technique that we talked about in the last couple of videos. But to do that, we're going to need one of those useful results that it's going to be helpful to put into our L1 cache along with the voltage divider rule and the current divider rule if we're interested in analyzing CMOS circuits like this. And this is the transconductance of a MOS transistor with source degeneration. Okay, so what do we mean by that? Well, let's say we have an NMOS transistor that's operating in saturation, like so. So it's got some saturation current flowing, let's say I sat, and we have some gate voltage being applied. And then the source is connected to something, and we're not sure what it is. We'll call it X. And that is characterized by a terminal incremental resistance of R sub X, where R sub X is going to be, if we call this the source voltage, and the same current I sat flows in here, this will be basically delta Vs over delta I sat. So in order for this current to increase by a little bit, the source voltage is going to have to go up by a little bit, and that ratio of by how much the source voltage has to move for a given change in current flowing into this terminal is this incremental resistance. And so if we were to apply a delta Vg to the gate here, the current I sat would increase by some delta I sat, but also that current has to flow out of the source and into this thing down here that's connected to the source. And so this will also have to increase by delta I sat, and Vs will have to increase by some delta Vs in order for that to happen. But notice that the initial increase that we might have expected based on the increase in the gate voltage is opposed by an increase in the source voltage. And so the transconductance of the transistor will be degraded or degenerated because the source voltage is also moving. So if the source voltage were held fixed, this delta I sat to delta Vg would just be little gm of the transistor. But because both the source and the gate are moving, we have to figure out what the effect of the source moving is on the increase in current we get. So we want to find delta I sat, delta Vg in this case, with this finite source degeneration resistor or resistance down here. Okay, so to do that, we're going to need a couple of things. One is the way that incrementally the saturation current behaves as a function of the delta Vg and the delta Vs. So the delta I sat is going to be given by little gm times delta Vg minus little gs times delta Vs. So you remember gm was di sat dVg, right? That's the partial derivative of the saturation current with respect to Vg. And so the increase in I sat that we get is going to be given by that first order partial times the delta Vg. And this GS is going to be related to di sat dVs with appropriate sort of sign conventions for the source conductance. And that's why the minus sign comes about. But this is basically just a tangent plane approximation to our EKV model for the saturation current, if you like. This would come by differentiating or expanding the EKV forward current in a tangent plane approximation about the point VGVS, and suppressing the constant term and just keeping the first order term. So that's what this is. This models the incremental properties of the MOS transistor in saturation. And then the other equation we have here, of course, is that delta I sat is given by incremental Ohm's law here. It's going to be, if we rearrange this, it's going to be delta Vs over Rx. So this comes from the MOS transistor, and this comes from whatever Rx is. Incremental Ohm's law on this thing connected down here in the source. And our goal here is just to eliminate the delta Vs, because we're not going to necessarily want to know for a given change of gate voltage what the source is doing. You know, for instance, in our diff pair, we change V1 or V2, and instead of having to figure out what the common source node is doing, we'd like to just be able to chain our way through and figure out what the increase in the current is quantitatively. And that's what we're interested in figuring out here, is a way to do that without having to solve for the source voltage and eliminating that. So we're going to eliminate it once, and we're going to put this result in our cache of useful results that we can apply without having to solve over and over again. Okay, so we're just going to solve this equation, the second equation for delta Vs. So delta Vs is equal to delta I sat times Rx and we can substitute that in here, and that implies that our delta I sat is equal to little gm times delta Vg minus little gs times Rx times delta I sat. We can just transpose this to the other side and collect the delta I sats on the left-hand side of the equation, factor that out, and we would get that delta I sat times 1 plus omega gs times Rx from this term that we transpose. And on the right-hand side, that's equal to little gm times delta Vg. And we can divide both sides of this equation by 1 plus gs Rx and solve for delta I sat. And that's little gm times delta Vg over 1 plus little gs times Rx. Okay, and so the transconductance gain of the transistor with source degeneration, which we could call capital GM, okay, that's the GM of this piece of the circuit, both the transistor and whatever is down here in the source. Delta I sat for delta Vg. And we just move the delta Vg downstairs, and we find that it's little gm of the transistor over 1 plus little gs of the transistor times Rx. And we can notice a couple of things here. One is that if gs and Rx are positive, which they will very often be, then this denominator is always greater than 1. And so relative to the transistor by itself, the transconductance gain of the source degenerated transistor is always going to be less than the GM of the undegenerated transistor, which is just up in the numerator. So we're taking the thing that's the undegenerated transconductance of the MOS transistor and dividing it by something that is larger than 1. And so we're always going to be degrading it relative to what it would be. The other thing is if we were to have an ideal voltage source down here holding the source fixed, or if this was connected to ground, for instance, well, the incremental resistance of a voltage source, or ground, is 0. And so if we were to plug in Rx of 0, we would just recover the ordinary transconductance gain of the MOS transistor. And so that limiting case makes a whole lot of sense. And if we were to think about having a current source down here, so that let's say we had something like an ideal current source down here biasing ISAT, that would have an infinite incremental resistance. And if we think about increasing the gate voltage in that scenario, well, the current is not going to increase at all because we have an ideal current source in series with our MOS transistor, and it's only going to let whatever current it's specified to produce through. And so that'll have an infinite incremental resistance Rx, and so we would get a GM of 0 because we'd be dividing little gm by basically 1 plus infinity here. And so those extreme cases check out with this formula, and it makes sense for positive GS and Rx. And so this result is going to be one of those useful things that we'd like to keep kind of handy for analyzing these incremental properties of CMOS circuits. Okay, so let's now apply this result to figuring out the differential mode gain of our 5-transistor diff amp using node fixing. Okay, so first we're going to do the GM part. So so 5-transistor Okay, so we're going to have our PMOS current mirror here. Diff pair. So we have V1 and V2. And we're going to assume that they're just a pure starting point is a pure common mode input. This is sort of the nominal 0 condition for us. And if you think about the way that an amplifier like this would normally be applied, it might have negative feedback around it. And so the negative feedback might adjust things so that the two inputs are the same. So I mean, this is a very common sort of nominal quiescent condition that we're going to be interested in. And we have a bias voltage down here, so we have MB, M1, M2, M3, M4, V3. And of course we know that the quiescent operating point for the output voltage is that Vout will be basically equal to V3 under these circumstances. So there'll be a balance here between Vout and V3. And what we're going to be interested in doing is applying our auxiliary voltage source to the output to hold the output voltage fixed. And we're going to be pre-adjusting this so that this is exactly equal to the quiescent V3. So that should be that when we connect it up to fix the output voltage, there should be no I-out flowing out of the circuit, no exchange between this test voltage source and the circuit. And what we're going to do is apply a little delta VDM. And we're going to assume we're going to apply it to the left-hand side here, to the M1 side. Strictly speaking, this is not a pure differential mode input voltage change because we're also changing the average value here by half of delta VDM. To make a pure differential mode input voltage change, we would have to apply half of delta VDM to this side and minus delta VDM over 2 to this side. And that would be a pure differential mode input voltage. And of course, we could handle that without very much difficulty just by using superposition. We can first apply that delta VDM over 2 to the M1 side without this one. Okay, applied. That would be the first component. And then calculate the response to the first component. Then take this one away and apply this one and figure out what is the delta I out due to this one. And those two would just superpose. And that's not too hard. We can do that. It turns out we'll get exactly the same answer if we just apply it all to one side. So that's what we're going to do. And if you'd like to try it yourself, to apply half to this side and half to that side to convince yourself that you get the same answer, more power to you. So we're going to be interested in what is the delta I out that flows out of the circuit when we apply our delta VDM. Okay? And so what we're going to do is we're going to track the current increments that we get as a result of doing this. Okay, so that's going to take a little bit of getting used to, but what we're going to do is we're going to say, okay, well, the first thing that happens when we put our delta VDM into the gate of M1 is that we're going to get an increase in the current I1 by some amount, delta I1, and we're going to have to figure out what that is. But before we do that, we're going to think about what happens to this delta I1 as it flows in the circuit. Okay, well, one thing that it's going to do is it's got to come from the input to the current mirror. And so the current mirror is going to increase its input current by delta I1, and that current increment is going to be mirrored by the current mirror and is going to flow here. And it's going to come out as output current. So it can't go into the drain of M2 because M2 is saturated, and if there's no early effect, then it's certainly not going to go into the drain terminal because the drain acts like a current source. But even with the early effect, you can also see pretty easily that all of this delta I1 is going to have to come out as delta I out because we're holding the output voltage fixed here for this part of the calculation, right? And in order for a resistor to change the current flowing through it, the voltage on it has to change, right? But if that voltage is being held fixed, then there's no change in the voltage across either an early effect resistor here on M4 or an early effect resistor here on M2. And so you can't get any additional current flowing in either of those two. And so all of that delta I1 is going to go for the output voltage source. Another way of thinking about it is you have a current divider. The current divider would be between any finite resistance connected here at the common drain node of M2 and M4. And you've got this voltage source here, and the current's going to go for the branch that has the highest conductance. Well, the conductance of a voltage source is 1 over its incremental resistance, and the incremental resistance of a voltage source is 0. So 1 over 0 would be a very large number, approaching infinity. And so all of the current is going to go for this branch. That's another way of thinking about it. Okay, so whatever way works for you. So we know that delta I out is going to have at least one delta I1 here. But we have to go back here and see what happens when this delta I1 comes out the source of M1. Okay, we have to ask what happens when it comes down onto this node V. Okay, well, it only has two places that it can go. It can go into the drain of MB, or it can go into the source of M2. Okay, and this is where it's going to get a little bit weird, okay, or it may take a little bit of getting used to. If MB is saturated and the early effect is negligible, the only place it can go is up the source of M2. Okay, if we do have an early effect resistor here, modeling a finite early effect on MB, then there's a current divider that happens between the source of M2 and the drain, or that early effect resistance modeling the drain conductance of MB. And we can figure out delta I1 times the current divider ratio. And the current divider ratio is going to be something like it's going to be like proportional to the incremental conductance of each of these branches. So we've got a GS and we've got an RO. And if GS-RO is much bigger than 1, then the GS is going to be a much bigger conductance than 1 over RO. And so 99.9% or 99% is going to go for the source of M2. And so we're just going to ignore the early effect on MB. And all of the delta I1 is going to go up into the source of M2. And it's going to flow out of the drain. And just like the delta I1 coming from M4, it's going to have to come out as output current. Now, having this delta I1 flow back up the source and out the drain of M2 is one of these things it's going to take a little bit of getting used to. Now, the current is still flowing from drain to source in M2. So there's still an IB over 2 that's flowing through M2 as the quiescent current. And what we're saying is that there's an equal reduction in I2 down from half of IB by the same amount that M1's current increased. Again, the diff pair currents are a zero-sum game. They have to sum to IB. And so any increase in the current in M1 is met by a current reduction in M2 of the same amount, or by the same amount. And so we can model that decrease in I2 by having a current increment flowing against the quiescent current. Okay, and that's what we're keeping track of on this diagram here, and that's what this means. So if we think about this current delta I1 flowing around here and back out here, it becomes very easy to do that. And so delta I out is going to be 2 times delta I1. So this is the GM part of the node fixing calculation. Delta I out is going to be 2 times delta I1. Well, now we're in a position where we have to figure out what is the delta I1. Well, we have a saturated transistor here, saturated NMOS transistor, and we have a finite incremental resistance connected down in the source. And so we can use the result we just figured out. And we have that this is going to be 2 times, well, it's the little gm of M1 times the delta VDM divided by 1 plus GS1 times whatever Rx is down here. And so we have to think about what is connected down here that makes up our cloud with the X in it in this particular case. Well, we have the drain of MB, which if we were to model its early effect, we would have an ROB, and that appears in parallel with the source of M2. And so we have a 1 over GS, that's the incremental resistance of the source of M2, 1 over its incremental conductance, would be 1 over GS2, in parallel with ROB. Well, again, if GS-RO is much bigger than 1, then that parallel combination will be dominated by the 1 over GS, the lesser of the two branch resistances. And so we could neglect that ROB and write this as 1 over GS2. Okay? But GS1 equals GS2 at their quiescent operating point because they're matched and they have the same current, IB over 2, flowing through them. And so those two incremental conductances will be the same. And so this will just be GM1 over 1 plus 1. So this is just 2 times GM1 times delta VDM over 2. 2's cancel, and we're just left with little GM1 times delta VDM. And so the GM of our 5 transistor diff amp as a whole is just going to be given by, delta I out over delta VDM, which is just little GM1. Okay, so that's half the calculation. So now we have to do the R out piece. Okay, and that's going to take a little bit of doing, but we can do it. So I'm going to take away our current increments here. And for the R out piece, what we're going to do is take our output test voltage source. So we've taken away our delta VDM to get the R out. And conceptually what we're doing is we're looking at increasing V out by some delta V out and seeing how much current delta I out flows back into the circuit. And the ratio of delta V out to delta I out is going to be R out. Well, immediately we can see that if we don't have any early effect on M2 or M4, there's not going to be any incremental current delta I out that flows back in here, because we've got the drain of a saturated M4 and the drain of a saturated M2. And so we're going to at least have to have the early effect of these two transistors to get a reasonable read on a finite R out. And it turns out that those are the only two early effect resistors we're going to need. I will try to loop back around and give you some intuition for how you can try to figure that out ahead of time, or some heuristics. But that's what we're going to do for the sake of time, is we're just going to assert that we're going to need the RO4 and the RO2. In order to make this work. And to facilitate the R out part of the calculation, we're going to actually apply source splitting, voltage source splitting, and superposition. Okay? So we're going to split this output voltage source into, in this case, 4 replica sources, one connected to the drain of M2, one connected to the early effect resistor RO2, one connected to the drain of M4, and one connected to the early effect resistor RO4. And we're going to then sequentially apply our delta V out to each of those 4 replica sources in turn, and figure out what is the component of delta I out due to each of those. Okay? So that is going to look like this. So we're going to have four replica sources. And we could number them, let's say, I don't know, 1, 2, 3, 4. These are all V out. And we're going to be interested in the total current that flows through this bundle of wires. And when we apply our delta V out, in principle, each of these 4 different delta V outs could excite a current in all 4 or any of these 4 wires. And so in general there are 16 possible components of delta I out. There could be 4 due to the delta V out on branch 1, 4 due to the delta V out on branch 2, 4 due to the delta V out on branch 3, and 4 due to the delta V out on branch 4. And so we have a numbering scheme that we're going to follow where we'll have a double subscripted index to keep track of these components. So delta I out ij is the component of delta I out in branch j, or branch rather I, due to replica source j. And so here's where the superposition comes in. We don't have to apply these 4 delta V outs simultaneously. We can apply them one at a time and then superpose all 16 components. So we're going to consider, let's consider number 1 first. Well, here we have this branch connected to a resistor. So we're going to accumulate the delta I out down here. So we have this branch connected to the early effect resistor R04, and so we're going to have a delta. Let's see if I can actually get this to fit. We're going to have a delta I out a delta I out in branch 1 due to the change in voltage on replica source 1. And that's just going to be given by the incremental Ohm's law for R04. So that's going to be the delta V out over R04. This is delta I out 1. Now, we have to ask ourselves, does that current do anything else? Does it excite any currents anywhere else in the circuit? Well, in this case, the other side of this resistor is just the power supply. And so this incremental current is just going to have to flow back to ground through the power supply. The voltage on the source of M4 isn't changing because it's hooked up to a power supply. And so there's no other current flowing in any of these other 3 branches due to this delta I out 1 flowing back to the power supply. And so there is no delta I out 2-1, 3-1, or 4-1. And so here we have we've considered 4 of the 16 possible components of delta I out, and 3 out of 4 of them are 0. And it turns out that that's the way that this works for the most part. There will be very few cases where we have a very dense matrix of these components. If you want to think of them as components of a matrix, it's going to be very sparse. And so now we're going to move on to branch 2. Or replica source 2. So what are we connected to here? Well, we're connected to the drain of M4, and M4 is saturated, and in this case, this is an ideal saturated transistor because we've encapsulated the early effect in this early effect resistor here, RO4. So this is the drain of an ideal transistor. And so it's going to act like a current source. And so we can change the voltage here all we want, and there's not going to be any change in the current flowing through branch 2 because it's an infinite incremental resistance. And so there's no delta I out 2, and there can't be any other effect in any of the 4 branches of the circuit either, because this voltage source is only connected to the drain of M4. And so all 4 of the components, possible components of delta I out due to the replica source 2 are 0. So we've considered half of the components, and 7 out of 8 of those components have been 0. Okay, now we're going to move. We're going to skip 3 for the time being because that's the most interesting one, and we're going to go to branch 4. And here, we're connected to the drain of M2, which is saturated. And again, just like with M4, M2 is an ideal transistor. So this is the drain of an ideal transistor because we've encapsulated M2's early effect in RO2. And so there is no delta I out 4 because we're talking to the drain of M2, and it's acting like a current source. And so all 4 components of delta I out due to delta V out on branch 4 are 0. So now we've considered 12 out of the 16 possible components, and 11 out of those 12 have been 0. And so now we move on to branch 3, which is the most interesting one. And so here we're talking to the early effect resistor of M2. And so there will be a delta I out to delta V out, delta I out 3. The delta I out on branch 3 due to replica source 3. And we can write down what that is, but we want to figure out kind of what happens to it as we trace it through the circuit. So it's going to come out down here on the other side of M2, and it sees a current divider. So that current is going to split. Some of it's going to flow back up M2 and come out the drain. So that will be a delta I out 4, 3. So here the current is flowing back against the positive sign of delta I out, so it's going to have a negative sign, okay, and it's going to be some fraction of delta I out 3, so it's going to be delta I out 3 times a current divider ratio that we can figure out. Okay, so bear that in mind. And the other place that this current can go when it gets here is going to be back up the source of M1. Okay, so if there's no early effect on MB, it can't go down the drain of MB. If we had an early effect resistor here, we could model the early effect on MB, and there would be a third place for that current to go. But it turns out that that's going to be kind of one of these 1% places that the current can go, because the source conductance of these 2 transistors is going to be much higher than the drain conductance of MB. And so we're going to neglect that ROB. And so this current that flows back up the source of M1, where's that going to go? It's going to go out the drain and into this current mirror. Okay? And that current mirror is going to mirror that current increment, and that's going to flow in to M4, and so it's going to be a delta I out 2, 3. And notice that that's flowing in. So this current's coming up this way, and the mirror is going to make the current flow in M4 in the same direction. And so that's going to be positive current with respect to the delta I out sign convention. Okay? So we have here 3 components of delta I out due to replica source 3. Okay? And so let's write those down. So our original delta I out 3,3 is going to be given by the delta V out divided by the incremental branch resistance here. And so that's going to be delta V out over, well, we see RO2 in series with whatever the incremental resistance is down here. Okay, so the incremental resistance that we see down here is going to be 1 over GS2 in parallel with 1 over GS1. And so that is delta I out 3,3. Of course, 1 over GS1 is going to be the same as 1 over GS2. And the reason for that is, again, because our quiescent operating point, which is where these GMs and GSs are calculated, is the balance point here where we have a pure common mode input. And so the two currents of I1 and I2 are going to be the same. They're going to be half of IB, and the GMs and the GSs are going to be calculated on that current basis. And so 1 over GS1 parallel 1 over GS2 is just going to be 1 over 2 GS1, and that appears in series with RO2. So that's going to be very nearly just delta V out over RO2 at the end of the day. We can, if we like, recognize that these two currents, the delta I out 2,3 and the delta I out 4,3, are each going to be proportional to the delta I out 3,3. It's going to be delta I out 3,3 times some current divider ratio. And then this one will be the delta I out 3,3 times this other current divider ratio. And so we can pre-factor out the delta I out 3,3 if we recognize that they're both going to be proportional to that. And so we can basically write parentheses 1, in this case minus the current divider ratio that gets us the delta I out 4,3. And so what is that? Well, the current divider ratio is going to be GS2, it's the conductance of that branch, divided by the sum of the branch conductances, GS1 plus GS2. That's going to be the current divider ratio delta I out 4,3 over delta I out 3,3. And then the delta I out 2,3, we're going to have a plus because it's flowing in to the amplifier. And that current divider ratio is going to be given by the branch conductance of the source of M1 divided by the sum of the two branch conductances. So GS1 over GS1 plus GS2. And this is delta I out 2,3 over delta I out 3,3. So this 1 here represents just the delta I out 3,3 term. So when we multiply this through, distribute it through this parentheses here, this times 1 gives us the delta I out 3,3. This times this current divider ratio gives us the delta I out 4,3. And this times this one gives us the delta I out 2,3. Okay, so that's how this works. Now, GS1 equals GS2 like we just said. Okay, so that has implications for what goes on down here, and also what's going on in here. So this is, if you like, GS, let's say GS1 over 2GS1, which is just a half. And this is GS1 over 2GS1, which is just a half. And so we get 1 minus a half plus a half, which is just 1. So even though there are 4 non-zero components of delta I out due to the delta V out of the 16, these two, the delta I out 4,3 and the delta I out 2,3, happen to cancel each other. And so really there are only 2 at the end of the day, non-zero components of delta I out in this circuit. Okay? So this is going to be approximately just given by, or this is exactly equal to, sorry, delta V out over RO4 plus delta V out over RO2 plus 1 over 2 GS1, let's say, because the two are equal to each other. And this is going to be approximately delta V out over RO4 plus delta V out over RO2. And this follows, this is approximately RO2. Maybe I should make this 1 over 2 GS2 if GS2 RO2 much greater than 1. Okay? So that leads us to the conclusion that R out, which is equal to delta V out over delta I out, we factor out the delta V out, and we get 1 over RO4 plus 1 over RO2, but that goes downstairs on the other side, and so that becomes just RO2 parallel RO4. Okay? And it's a little more subtle than just looking into the output of this circuit and seeing, oh, we have M2, the drain of M2, in parallel with the drain of M4, and so it's just RO2 parallel RO4, because we do have to think about what's going on here at the common source node and what's going on with the other side of the circuit and everything, but that's what it boils down to. So it's very simple. It took us a little bit to get there, and so the differential mode gain of the circuit as a whole we get through node fixing by multiplying the GM of the circuit as a whole with the output voltage held fixed. So ADM, which is delta V out over delta VDM, is equal to the GM times the R out. And we figured out that the GM was just GM1, and that the R out was RO2 parallel RO4. And so what kind of number is this? Well, this is a number. If RO2 and RO4 are kind of on a par with each other, then the parallel combination of them would be about half of either one of them. And so we'd have a GM times something like half of the incremental output resistance of a transistor that's matched to M1. And so it's sort of like the intrinsic gain of our NMOS transistor, half of the intrinsic gain of our NMOS transistor in the diff pair. And so it's going to be a number that's on the order of maybe somewhere in the 100 range, a few hundred, something like that, or maybe several tens if we're up in strong inversion. And so we have the common mode gain was delta V out over delta VCM, we said that that was minus kappa over 2 times 1 over GM3 ROB. And this was a number that was kind of on the order of 100. And this was a number that was on the order of minus 0.01. Something like that. So this would be something like, let's say, 40 dBs. This would be a number that's something on the order of, the magnitude would be something on the order of minus 40 dBs. And so the ratio of these two things, which is called the common mode rejection ratio, often expressed in dBs, would be basically 40 minus a minus 40, which is 80 dBs. So that means that this 5-transistor diff amp has a preference for differential mode signals that's about a factor of 10,000 higher than it is for common mode signals, which is pretty awesome. Okay, so we've gone a little bit longer than I might like. Hopefully that that was helpful. And there'll be another video tomorrow for Tuesday, but hopefully won't be quite as long.